It's great for our
Sorry?
we just shared the
Mhm.
springs on the
Oh, yeah.
black box.
Yeah. Good.
So, any outlets to turn selective? No, okay. So it's a
Probably-
multiplies recently, so
Yeah.
okay.
Sorry. I have no idea.
to make someone coding.
Sorry?
It could cause is it a laptop you're controlling, right?
Yeah, but it's as you can see, look, it's an extended screen.
Oh.
So I don't actually see it.
So if I see anything, any problem with the screen, can I just like raise your hand?
Yeah.
Like what's the measurement?
But it won't happen. This happened because I
Oh, yeah,
made
just
this laptop. When you're gonna be presenting, I'm not gonna touch it.
Oh,
Nothing gonna happen.
Just include that.
Yeah, don't worry. Yeah. The mic on the podium, people when they speak, they usually they get too scared that they are too low, so they come really close to the mic. But when you come too close to the mic, there's a lot of sound. So don't worry about that. You can just stay back and speak louder, and I'm gonna push you up, make it loud. But if you're too close, I cannot, reduce the popping sound. So just speak normally. You don't need to be that close. Just,
Thank you for
no
the
worries. No worries.
Thank you very much for joining us today. So my name is Yan Chen, and I'm a faculty member at the University. Today we are super excited to present this program and spend the next 3 hours with all of you on this topic of retrieval-based models and the applications. So first of all, please let me introduce this group of fantastic speakers who have been actually doing almost the work for this tutorial. They have been doing a lot of effort for the tutorial today, and you will see all of them soon. So this includes Karen Asai with a PhD student from the University of Washington. Sewon Li with also a PhD student from the University of Washington. Zhou Xuanzhong with a PhD student from the University. Okay, so next, please let me talk a bit about how we can organize the product today and how we hope that we can participate in the product. So first of all, we have already put all our slides and also the reading list on this website. So you can directly go to ACL 2023, retrieval-based.github.io. So if you haven't already downloaded those slides in the last 1 day and 2 days, so we also encourage you to check out the latest version because we have made some small changes. Actually, I've seen a lot of lessons in version. Also, it says there has one of them. That is voice line better.
Sorry?
Yeah. So throughout
The
this
echo.
part, so our plan to provide a Q&A, that's how the whole process is like. So you can easily go to this tiny
Monitor the Zoom chat and see if they can access the
QR code. So basically, if you have any questions, either detailed clarification questions or
Sorry?
Let me know if it's not.
we encourage you to put your questions.
No. Okay.
Or questions. So just due to the time constraints, we have not been able to talk a lot during the presentation, but we will do our best to address questions in the slide. And then once we have reserved time at the end of both the first part and the second part, so we will also have time to address questions.
No.
So let's dive into the topic today. So what are retrieval-based learning models? So some people also refer to these models as retrieval-augmented learning models. So today we'll just use these two terms in this article. So basically, retrieval-based learning models essentially combine the two key concepts. One is retrieval, secondly, learning model. So a retrieval-based learning model is actually a learning model. So we all know what a learning model. So given the previous context, x, y is 2, x minus 1, along the model gives you a probability distribution of probability the next open. And in this example, the capital C and the comparable is so the model which second model give you a high probability for the word Toronto. And in this part, we also broadly extend this definition to either math learning models, such as version. All that we call models like models. And the second key component of the retrieval-based models is that we also assume these models we can treat from our large current data, at least in the infrastructure. As you can see on the video. So besides the standard component of long-term models, these models also need to retrieve from this data store to pull out some more relevant information to help us make more accurate predictions on the next. So in some contexts, people also refer to standard language models as parametric models because these models are actually just implemented as large neural networks. But we also refer to retrieval-based models as either semi-parametric or non-parametric models. So let's put things a little bit more in context. So in the past 3 or 4 years, we have seen amazing developments in this space of machine learning models. So the figure on the left shows a lot of major machine learning models up to March this year. So you probably all know about this part because these models include like ChatGPT, GPT-4, and many others. And all these models essentially are all fully parametric. And they are all built based on transformer networks. And all these models are at least trained with that's open prediction. And some of these models are optionally trained with the reading was learning from human feedback, but we will not talk too much about this part. And then also like actually on the model is that in the last like few years, even the model size, all the number of data and use and models are getting bigger and bigger. And of course, you have to set on points. And at the same time, we also in this community, we also have seen a lot of exciting developments for the developing Retrieval-based models for knowledge enhanced tasks, including like open domain philosophy, and many others.
Навіть всі мікрофон не говориться, але
It's a main out.
On that average, small as usual, including forward ANCs and also shots. So we also have a little bit about what's the short is. So now the key question is, if these two fields both have so long and exciting developments, so why do they actually why do we want to have both Retrieval and not
Оце недобре сторону. Ovo je tvoj laptop, ovo je production.
Да, я бачу шері, а не тут свій лаптоп.
Gle, možeš ga odavde miti, pa si ne moraš naći. Ajde probaj.
Не, пам'ятаю, воно ще раз скрін сходить.
Project sve, možda nekom drugom, možda nije on. Čekaj.
But they actually make a lot of common questions. People from us. So let me give you an example. So you have ChatGPT. These 5 important papers often by ChatGPT. So we all know that ChatGPT and people give a keynote talk in the world.
Що воно це твій мобітел ти.
Excuse me, for those on the Zoom, please mute yourself.
So this is called ChatGPT process. So papers by ChatGPT. Number 1, learning internal conversations by error computation. So this published in 1986. So this is a famous aggregation paper. So that's correct. Number 2, deep movement machines published in 2009. This is also correct answer. So ChatGPT just keeps listing. So this is the number 4 answer. So ChatGPT says about this type of deep learning, cause exponential and error will published in 2016. But this is something actually not correct because this book was actually false in so this is actually not correct. So number 5, potentially unique. So we all know that it's a transformers. But unfortunately, Hinton actually not about us. So we all know that Jeffrey Hinton is such a problem scientist. But if we just replace Jeffrey Hinton by some other
Вест, нещо.
So this problem has been actually well characterized. I just see what ACL times 3. So in this paper, the basically not much of the model is just a simple prediction pattern that only has the problem of observation. So all you need to do on the treatment is all the blue parts that are historically by the popular intentions. So you can see just at the 3 decimals blue bars. So even the best, not the best, even the larger GPC dimension is using 3 modules. Since this model are only able to achieve 100%.
Jel, ti vidiš da tamo? Možeš povući, taj prozor, ja ne mogu.
So that's the relation problem here. the large language models have memorized a great amount of knowledge. The knowledge can actually easily get outdated and very difficult to update. Here's another example. So who is the CEO of Twitter? So ChatGPT will tell you, as of my knowledge cutoff in September 2021, the CEO of Twitter is Jack Dorsey. The answer was correct in 2021. But we all know that Twitter actually has changed a number of CEOs in the past 2 years. So just a couple of days ago, they actually got a new CEO. Actually, this lady, Linda Yaccarino. So there's no way that ChatGPT is able to figure out the correct answer for this question. And this is actually a very active research field, and a lot of work trying to actually study how to edit the parameters of the neural networks to update with the up-to-date factual information. However, these models are still far from being scalable and effective. But today, if we have a retrieval-based language models, so a big advantage for these models is that you can easily just update and expand this data store with up-to-date information. Sometimes you even don't need to do any retraining. You can simply just replace this data store with newer information. So we just talked about the large language models are easy to hallucinate. So another key challenge of the large language models is that their outputs are essentially inherently not interpretable and also very difficult to verify. But if you have a retrieval-based language models, because the retrieval-based language models have this retrieval module, so we can actually look at and inspect the information, the knowledge source from the retrieval results. So this model, by constructions, can actually provide better interpretability and controllability. This has also enabled a line of new research by generating text with citations. So if you can actually retrieve a lot of information from relevant information from large corpus, you can actually incorporate the retrieval information in the text generation process, as well as providing the references to the retrieved documents. So this could actually provide a much better interface for users to verify whether the information is correct or not. And this pattern has been super powerful and also has already been in production. So here the screenshot we took from the Bing chat. So if you ask Bing chat, create an itinerary for exploring Toronto for 2 days. So the model is not, the system is not only just able to give you a long output, but it can also provide you this references, which are actually the links to these web pages that actually come from the search engine of the Bing search engine. So this is actually really, really a powerful paradigm. Okay, so another key limitation I want to briefly mention here is that also recent work, a lot of recent works actually show that large language models are also very easy to leak private training data. As this Carnini et al. 2021 paper shows that if you prompt the GPT-2 in a smart way, so these models actually very easy to spit out some private user information from the training data, including address, email, and phone numbers, and so on. So a lot of people actually believe that retrieval-based language models actually provide a good solution to this problem, because you can actually just use a public language model and put your private data in the data store. So the users can just build their own retrieval-based language models on their private data locally. So this actually provides a good solution. Okay, so finally, I want to talk a bit about a more high level, more long-term and big picture goal of the retrieval-based language models. So we all know that large language models are very large. So that really means that they actually require a lot of compute and money to actually train these models and even for deployment. But if we have the retrieval language models, our hope is that eventually, if we can have a smaller language model paired with a very large data store, we hope that this model eventually can be actually equally competitive with a very large parametric language models.
So this is actually a very challenging research question. Arguably, probably $1 billion question right now. So if we can eventually achieve this goal, this paradigm probably can provide a really like a powerful paradigm to reduce the training and inference cost greatly. But we are not there yet. Although some work actually, including this Rachel paper, they claim that the Rachel model can, by using a very large data store, they can obtain comparable performance to GPT-3 on the pile data set using only 25 times fewer parameters. Again, this actually shows some promise, but we are not there yet. And we believe that this still remains as one of the most important goals of developing retrieval-based language models. Okay, so before I conclude this part, I would like to also talk a bit about the goals of this tutorial. So in this tutorial, we will cover a number of the key developments on retrieval-based language models. So most of the papers that we are going to cover actually came out in the last 3 years, and many of them actually just came out in the past year. So we are going to start with the problem definition, and then we'll go through like the architecture design and the different training methods, and also a number of the applications and extensions of the retrieval-based language models. And I want to emphasize that, so this tutorial is actually very cutting edge. And although all of the presenters here have been actually working in this space and thinking about this problem for quite a bit of time, but we are still far from understanding how to best develop retrieval-based language models compared to the parametric models. So we hope that through this tutorial, we try to do our best to provide some taxonomies of the existing research and provide some key insights from the existing research. We also hope to provide our perspectives on the current challenges and also the open problems. So we hope that after this tutorial, there'll be more and more people interested in working on these problems. And we hope to see actually much better progress moving forward. Okay, so finally, here is like an overview of the schedule today. So after the introduction, Se-Wang will talk about the problem definition and also the architecture design of the retrieval-based language models. And then it will be followed by Zexuan, who will talk about the training methods of retrieval-based language models. So we'll have like a 30 minutes coffee break in between. And everyone please just come back at 4 p.m. and we'll continue the training methods of retrieval-based language models. And later on, it'll be followed by Akari, and she'll tell us more about the applications and the extensions, followed by a conclusion. Finally, I just want to mention again, so we will have time for Q&A at the end of both the first half and the second half. But if you have any questions, please post the questions on Slido, and we'll do our best to address your questions. Okay, so this is all I have. So without further ado, let me hand the stage to Se-Wang. Yeah.
Hello, everyone. Thanks for coming. I'm Se-Wang Min, and I will go over section 2, definition and preliminaries for retrieval-based language models. We define a retrieval-based language model as follows. It is a language model that uses an external data store at test time. So we have a language model and an external data store. So let's look at them one by one. Let's start from a language model. A language model is a model that outputs a probability distribution over a possible output vocab. For instance, we are given a prefix like the capital city of Ontario is, and we feed into the language model that is often based on multiple layers of transformers and output a probability distribution for which token to come next. So here, Toronto is assigned 0.52, and Ottawa is assigned 0.31, and there are other probability values which will eventually sum to 1. We can categorize the language model based on a few dimensions. For instance, there is an autoregressive language model that is given a prefix and make a next token prediction. And there is a masked language model that is given a text with a few masks and fill in the blank. We can also classify based on the architecture. So there is an encoder-only model. There that is based on a bidirectional transformers. There's a decoder-only model that is based on a unidirectional transformers. And there's encoder-decoder, which has both. If not specified otherwise, a language model refers to an autoregressive model based on a decoder-only architecture. But throughout the tutorial, we'll cover other types of models as well. A nice property of a language model is it can solve many NLP problems that we care about by casting those problems into a sentence completion task. And this is often called prompting. For instance, we can figure out the capital city of Ontario by feeding the capital city of Ontario is and make a next token prediction. We can also classify whether a review is positive or negative by feeding a review, and it was, and see whether the next token is likely to be great or terrible. Similarly, we can do translation like hello in French, and also ask an arithmetic question. A language model can be evaluated in either language model perplexity, which is given a raw text corpus and compute a negative log likelihood of every token in the corpus. Or it could be evaluated with an accuracy on a downstream task you care about. You can either do zero-shot or few-shot prompting, or you can fine-tune the model on the label data and compute an accuracy. We'll cover more in the later section. So we've talked about a language model. Now let's talk about an external data store. By default, a typical language model uses a large-scale training data to train the model and updates the parameters. And at test time, it discards the data and only uses the model parameters to make a prediction. The key idea of retrieval-based language models is to use an external data at test time as well. So here's how the inference stage looks like. First, there is a data store, and it often consists of a raw text corpus. It's very large scale, consisting of at least billions or trillion tokens. And it's a raw data, meaning that it's not the labeled data or not the structured data. And next, there is an index. And what an index essentially do is it takes an input, which we call a query, and outputs a small subset of elements in a data store that is the most similar to the query. What does it even mean? So in order to understand the index, let's talk about a similarity score. It is a score that represents how similar two pieces of text is semantically. We can define similarity score in many ways. For instance, it could be based on heuristics, which consider the lexical overlap between two pieces of text. Or it could be learnable. For instance, we can use the neural encoder that maps the text into the dense vector, and the similarity score would be an inner product between these two vectors. There is an entire field of research on how to define and learn the similarity score better, which we'll talk at the later part. Given the similarity score, now we can define an index. It's given an input Q and returns a subset of elements in a data store that has the highest similarity score to the query. So the returning value is basically K elements from a data store. When the data store is extremely large, this process can be very slow. So we typically employ a fast nearest neighbor search that approximate this process. And it can be an active area of research on how to do this fast and accurate. We will not go over too much detail here today, but there are many public softwares available, such as FICE and SCAN. There are many types of indexes. Some of them are exact search, which does not do any approximation, but it can be very slow when the data store is large. So we typically do an approximation that is relatively easy to scale to over billion scale. There's also a CPU search or a GPU search, depending on which resources we have. You can find more information in the FICE wiki page. So for today, we'll assume that we have a pretty good fast nearest neighbor search algorithm that is given to us, and then discuss the rest of the process. And typically we call a retrieval system, we refer to a retrieval system that's a combination of a data store and the index. So once we have this retrieval result, we now have to incorporate it into the language model and make a final prediction. So that's the overview of the inference process, but this may raise a lot of questions to you. For instance, what exactly is a query? And when do we use retrieval? What exactly are we retrieving from the data store? What's the element? And how do we incorporate retrieval result to the language model? So these are the questions that we will answer throughout section 3. Finally, I'll just introduce some of the notation. So we use X and Y as the input and output to the language model, and Q as a query, and D as a data store. Cool, so that was section 2. Now I will move on to section 4, where we discuss architectures for retrieval-based language models. Okay, so we can categorize retrieval-based language models based on 3 key questions. First, I'll move on. The first question is, what do we retrieve from a data store? For instance, is it text chunks like passages? Or is it tokens? Or is it something else? The second question is, how do we incorporate retrieval result to the language model? For instance, do we incorporate it in the input layer or the output layer, or somewhere between in the internal stage of the language model? And the last question is, when do we use retrieval? For instance, when you want to generate a sentence like that, do we retrieve only once in the beginning? Or do we use retriever for every token prediction? Or can we do somewhere in the middle? So in this section, I'll go over some of the key papers and categorize them based on these 3 questions. And here is the roadmap. We'll first start from the most simple and intuitive model that retrieves text chunks from a data store and incorporate it in the input by concatenating the retrieved text chunks with the original input. And we'll do it only once. We'll discuss RAM, which is one of the first paper that uses this approach. We'll then see how we can generalize it to retrieve every n tokens for language modeling. Next, we will see how we can incorporate retrieval to the intermediate layers of transformers instead of the input layer. We'll discuss the retro paper. And lastly, we'll discuss KNN-LM paper, which retrieve tokens from the data store instead of text chunks and incorporate them in the output layer. And finally, we'll discuss some of the other papers that provide extensions of this approach. I want to remind you that this is about architecture at inference time. We'll not go over anything about training, but it will be discussed in the next section. Okay, let me start from the first paper, RIAM. This is one of the first papers that use retrieval together with a language model. RIAM is a mask language model. So it's given an input text with a mask, like World Cup 2022 was the last with 32 teams before the increase to blank in 2026. So the blank is likely to be a number of teams in the future. And what a typical language model would do is to feed this input to the model and fill in the blank, like 48. What this model does instead is to feed this input to the retrieval system that consists of a data store that has millions of text chunks like passages. And it will retrieve top K chunks of text that are most similar to the input. And these chunks of text are incorporated by concatenated with the original input, fit into the language model, which will fill in the blank. And now you can see that this consists of 2 stages, the retrieve stage and the read stage. So let's go over each stage in more detail. First, it's a retrieve stage. So the data store is constructed based on Wikipedia, and it has 13 million chunks of text, which are basically passages. Each chunk is fed into the neural encoder that maps the text into a dense vector space. So we'll have a vector space like this. At inference time, given an input, we will feed this to the same encoder to map it to the same vector space. And we can employ a fast nearest neighbor search to retrieve top k chunks. In other words, we will obtain Z1 to Zk, which are key retrieved chunks that has a highest similarity score to the query. And here, the similarity score is an inner product between these two dense vectors. Once we have these retrieved chunks, now we need to incorporate it to the language model. And how it works is it concatenates each of retrieved chunk with the original input X, fit into the language model, and obtain the output distribution from each. So we have k different output distributions, and we can aggregate them by taking on weighted average. In other words, the output can be expressed in this equation, where the first term is from the retrieve stage, so it represents the similarity between the chunk and the input, and the second term is from the read stage. And we are marginalizing over every chunk in a data store. But since this data store is very large, we'll need to do some approximation. So you can think of k nearest neighbor search as some sort of approximation where we only consider top k chunks and all the other chunks are considered to have zero similarity to the input. Okay, that was REM. So to summarize, REM retrieves chunks of text from a data store. It uses retrieval in the input layer of the transformer since it is concatenating the text in string. And it is using retrieval only once. Just as a context, REM introduces lead to a few concurrent and subsequent work that follows a similar approach. For instance, there is DPR, which uses a different training approach, fine-tuned on open domain question answering. And there is REC, which uses causal language model instead of masked language modeling, also fine-tuned on open domain question answering and knowledge intensive tasks. More recently, there is Atlas, which also uses a joint training between retrieval and language model. We'll see more in the later section. And as you can see from this slide, most of the work focuses on knowledge intensive tasks like open domain question answering using fine-tuning. Perhaps surprisingly, it is rather recent where people started to use this approach for more generic language model and report perplexity. So we'll cover a series of work that does that. We call it retrieval in context language model. It's an autoregressive language model. So we have a prefix. Work of 2022 was the last with the 32 teams before the increase 2. And we want to predict a few of the next tokens, which likely to be discussing about number of teams in 2026. So what this approach would do is to feed the input to the retrieval system that again consists of many chunks of text in like Wikipedia and get the top one chunk that is most similar to the input. Then it is concatenated with the original input, fit into the language model and make predictions for the next n tokens. So you can see this is pretty much similar to REM. And the paper shows that it indeed improved perplexity consistently over different sizes of language models. One of the new questions that is raised in the context of causal language model is it necessary to use the entire prefix as an input to the retrieval system? For instance, imagine that you have a very long query like this. So it's talking about the game between USA and Iran in 2022, and then have some long sequence, and then end with 32 teams before the increase 2. So the tokens to generate is still likely to be about the number of teams in 2026. A naive approach is to feed this entire thing to the retrieval system and get the top one chunk of text. However, it is likely to be not really related to the number of tokens we have to generate because the majority of the content is about 2022 and it doesn't really talk about 2026. So what you might want to do instead is to take some of the latest token from the prefix and use it as a query to input to the retrieval system. and it would retrieve a chunk of text like this. And here you can see that this is more relevant to the tokens that we want to generate. And indeed, this paper showed that using a shorter prefix, especially more recent tokens, is more helpful. Although you don't want it to be too short because then you're losing the context. The second question you may have is how frequent should we use retrieval? For instance, let's say you have a prefix, workup 2022 was the last with, and you want to predict the next 12 tokens. Then what you would do is to feed into the retrieval system, get the top one chunk, concatenate it with the input, feed into the language model, and generate 12 tokens. And if you see this, you can see the earlier part is successfully covered by the retrieval system, but the later part is not really covered because it is already not relevant to the original query that we used. So what you might want to do instead is to generate 6 next tokens only, and then create a new query that has both the original prefix and new tokens, feed into the retrieval system, and get a new set of text chunk that is relevant to the new query. And then you concatenate with the input and feed into the language model to generate the rest of the 6 tokens. And in this case, you can see that the new retrieval result can cover the tokens to generate because this updated query makes it more relevant to the tokens to generate. So the paper shows that indeed retrieving more frequently improves performance consistently. However, it is important to note that this comes with an additional cost in inference time because for every additional retrieval step that you use, you need to do forward pass over language model. And this can be very expensive, especially when the language model is large. Okay, that was retrieving context language model. To summarize, they retrieve chunks of text from a data store and use them in part of the input layers, just like realm. However, they retrieve every n tokens instead of once. So compared to the previous approaches that focus on downstream tasks like question answering, we see that applying the similar approach to language model raised new questions like how frequent to retrieve and how to make the query. So far, all the approaches we discussed use retrieval as part of the input layer. However, as we briefly saw, this can be very inefficient at inference time if we want to retrieve many text chunks more frequently. And this is because for every chunk of text that was retrieved, we need to do forward pass over the language model. So our next question is, can we do it more efficiently? That motivates our next paper, Retro. Retro uses retrieval result in intermediate layers of transformers instead of the input layer. And they designed this architecture in a way that it can process many chunks frequently and more efficiently, as we will see very soon. Another finding from Retro that is sort of orthogonal to the architecture design is they managed to scale the data store to about 2 trillion tokens and show that this is critical in performance. So let's look at how Retro works. It is a causal language model, so it's given a prefix and want to predict next tokens. First, they cut the prefix into multiple splits. In this case, x1 to x3. Each split is fed into the retrieval encoder to map into the dense vector space. And we use key nearest neighbor search to retrieve top k chunks of text that is most similar to each split. We can fit them into another encoder to map them to some tensor representation of retrieval result. So each of E1, E2, and E3 is some 3D tensor that represent the retrieval result for each split. So these are the retrieval results, and how can we incorporate that to the language model? This is how the regular decoder-only model looks like. It has an embedding layer at the bottom, head at the top, and in the middle, they have L layers of transformers that consist of the attention layer and feed-forward network. What retro does is it has an additional block called chunk cross attention, CCA. And this takes E1 to E3, the retrieved tensors, as additional input to the model so that it can incorporate retrieval result. We will not go over too much detail on chunk cross attention, but intuitively what it does is to compute a cross attention between the retrieval result and the representation from the previous layer. So for instance, here we have a cross attention between E1 and some part of the vector from the previous layer. And we have another cross attention between E2 and the other part of the vector from the previous layer. And they're aggregated at the end and fit into the next layer of transformers. And the key idea here is that this cross attentions operation can be computed in parallel. For instance, imagine that you generated until this blue part and you want to generate the yellow part next. Then what you would do is to compute E2 from the blue part that you just generated, and then compute this part of cross attention. However, you don't really need to recompute this part, including E1 and other part of cross attention, because they were already computed to generate the blue part, and they can largely be reused. And this is how chunk cross attention can enable retro to process many blocks frequently more efficiently. Here's the result from the retro, and they report perplexity, so the lower is better. They show that retro can match or outperforms previous language models. In particular, they managed to scale the data store to 1.8 trillion tokens and show that this can lead to significant improvement in perplexity. Their oblations also show that the gains by using retrieval is constant across different sizes of the model. And as the data store gets larger, the increase can be even better. Okay, here's the summary of the retro. It retrieves chunks of text from the data store, and it uses retrieval result in the intermediate layers of transformers. And it can retrieve every n tokens, which is defined by how you split the prefix. So these are the three approaches we saw. And compared to the earlier approaches that use retrieval as part of the input layer, retro has a few advantages. It can process many blocks more frequently, more efficiently. It has some downside as well. For instance, it comes with some additional complexity, as you can already tell. And since it modified the internal architecture of the transformer, it cannot be used without dedicated training. Okay, so all the three approaches we see here are retrieving text chunks from the data store. What else we can use as elements in a data store? We will talk about KNN-LM that uses a different approach. It retrieves tokens from the data store instead of chunks. So you can think of it as a model that outputs a non-parametric distribution where every candidate vocab is every token in the data. And it can be seen as an incorporation in the output layer because it will output a KNN distribution and then incorporate it by using an interpolation. We'll see it very soon. So let's discuss how the KNN-LM works. This is a causal language model. So it's given a prefix like Obama's birthplace is, and we want to predict the next token. What the regular language model would do is to feed this prefix into the transformers that will convert it to some vector representation and send it to the softmax layer that will give a categorical distribution over every possible output vocab. What KNN-LM does is as follows. It has some raw text corpus like this and construct a data store where every target is every token in the text, and the key is a prefix that comes before the target. For instance, the first element here is constructed based on Obama was senator for Illinois, where Illinois is a target, and the text that comes before that is a key. So the important part here is the size of the data store is a number of tokens in the corpus, not the vocab size. So it can be easily over billions. Once we construct a data store, we can get the representation from every prefix in a data store, just like we did for the test input. So the question KNN-LM asks is, which tokens in a data store are closest to the next token that we want to predict? Because if we can figure this out, we can convert it to the output distribution. And this is essentially the equivalent to another question, which prefixes in a data store are close to the prefix we have. Because if the prefixes are similar, the next token is likely to be similar. And this is again equivalent to another question, which vectors in a data store are close to the current vector we have, because these vectors are representation for the prefix. So that is how the KNN-LM works. It tries to find the closest vectors by computing a distance between the current vector and vectors in a data store. It will get some k-nearest neighbor search to negation and normalization to convert it to the valid probability distribution. In other words, KNN distribution can be expressed in this way, which consider the similarity between the given prefix and the prefix in a data store. And the similarity score is computed based on the representation of the given prefix, the representation in the data store, and some distance function. So this is how KNN distribution is computed. And normally in practice, we can do interpolation by combining this with the original distribution. So here, this is a distribution from the regular language model. And this is a KNN distribution. And we can interpolate them by using a hyperparameter lambda. So this is how KNN-LM works. But you might be curious, why do we want to do that? Well, here's one example. Let's say we have a data store like this, and it has two elements whose targets are chip. But if you read this text, you can see that they are used in very different contexts. The first one is used in a positive context, and the second one is used in a negative context. So although they share the vocab, they're actually very different tokens. And if we map them into vector space, they will be mapped to very different places. So the language model can successfully distinguish them. Similarly, we have three elements whose targets are torch, but the first one is a machine learning torch. The second is a portable fire, and the third is a medical terminology. So even if they share the vocab, they're actually very different tokens. And again, when they're mapped to dense vector space, they will be mapped to very different places. And by employing these vectors, the KNN-LM can be more expressive. Here's the result from the paper. They reported perplexity, so lower is better. There is a regular language model baseline, and the same baseline that is 30 times larger. And the blue line is KNN-LM, where x-axis indicate the size of the data store. We can see that KNN-LM outperforms no retrieval baseline by a significant margin. And it gets better as the data store gets larger. The ablation also showed that if you increase K, which means your key nearest neighbor will be more accurate, then performance can be better. And it helps more when tested out of domain. And this is because we can use in-domain data store even if the model parameters were not trained in domain. This is possible because data store is much easier to replace or manipulate. Okay, so this was KNN-LM. To summarize, it retrieves tokens from a data store and incorporate the result in the upper layer since it gives some distribution and then combine with the regular language models distribution at the very final stage. And it has to retrieve every token because it can only predict a single next token. So compared to the other earlier approaches that we saw, retrieving tokens have some advantages. It allows more fine-grained retrieval, so it can be better at handling rare patterns or out-of-domain generalization. It also can be more compute efficient as long as KNN search is fast because there is no cross-attention between the input and retrieve text. However, one of the significant downside of KNN-LM is it's very expensive in space because given the same amount of text data, the size of the data store is number of tokens instead of the number of text chunks. And of course, the number of tokens is much larger than number of text chunks. For instance, in Wikipedia, it's about 13 million versus 4 billion. Another downside is that there is limited interaction between input and retrieval results, so it can be less expressive. Okay, so these 4 papers are the key papers we discuss in more detail. Now let's talk about some of the extensions. The first question we will ask is, so far all these approaches are deterministic on when to use retrieval or not, so it's fixed. But can we do it more adaptively? For instance, can we use retrieval only when it's necessary and skip retrieval when it's not? And that can potentially improve the inference speed. So we can use this adaptive retrieval idea either for text chunks or for tokens. So let's look at them one by one. One of the papers that followed this idea is Flare, and it used adaptive retrieval in a sentence level. Here is how it works. You're given an input, and the model generates one sentence without retrieval. So it's from the language model only. And then it determines whether to use retrieval or not. So in this case, the model somehow decided that they can skip retrieval, so it will finalize generation and move on. Next, it generates the second sentence. And here, the model somehow decided that they're unsure and want to use retrieval. Then they process the generation, fit into the retrieval system, get the top one text chunk, fit into the language model, and generate the second sentence. And this is going to be the final sentence. This can be done iteratively until the generation is completed. We can do adaptive retrieval of tokens as well. For instance, let's say you want to generate a sequence like this. Joe Biden graduated from the University of Delaware. What the KNN-LM would do is to use retrieval for every token prediction. And it can be very expensive because the search can be expensive. So what you might want to do instead is to skip retrieval when it's not necessary and use retrieval only when it's necessary. For instance, you might think that predicting from graduated is not really necessary. We can do it without retrieval. And predicting a period at the end of the sentence does not really require retrieval. And there can be multiple possible implementations of this, but one of the possible implementations is we model lambda as a function of the input x. So it's not deterministic. It can be based on how necessary the retrieval is. And if the lambda is smaller than some value, we drop it to 0. And this is equivalent to dropping KNN at all and just use the language model. So another idea to use adaptive retrieval is to use local information from a data store. Imagine you have a data store like this, and you're given a prefix, Joe Biden graduated from. Then what KNN-LM would do is to retrieve from here, University of Delaware. And you can see that we are sort of retrieving the token from the same sentence. So it may be not necessary to do KNN search every time. What you might want to do instead is to retrieve the very first token, but then afterward, you just follow the pointer from the data store to complete the sentence. And in this way, you retrieve only once and save other searches. Cool, so these are different approaches for adaptive retrieval. It can be done in either text chunks or tokens. And as you can see, this can be more efficient because by skipping some retrieval steps, it can improve inference speed. One downside of this is decision on whether to use retrieval or not may not be optimal because maybe this decision can be made only by looking at the retrieval result. So these are the different approaches we see so far. And they either retrieve text chunks or tokens. So you might be curious, is there other elements that we can use? So let's take a look at some of them. One idea is to use entities as elements. What are entities? These are real-world objects that have unique names, such as countries, locations, persons, or books. And the key idea here is that each entity can be represented as a dense vector in some dense vector space. And these vectors can be incorporated to the language model because these vectors hopefully have some background information about the entity. One of the papers that use this approach is entities as experts. So let's take a look at this paper. Here is how the regular language model without retrieval looks like. It's based on transformers layers. In entities as experts, there is a data store called entity memory, and it has one vector per entity. And this can be incorporated into the intermediate layers of transformers. For instance, as the input has Charles Darwin, we can take the vector that corresponds to Charles Darwin and incorporate it to the transformers layer. One nice thing about entities as experts is that the data store can be much more efficient because there is less number of entities compared to number of chunks or tokens. For instance, there are 6 million entities in Wikipedia. However, it has some complexity. For instance, the vectors for entity has to be learned separately, and it requires text with entity detected, such as text with hyperlink. And it also requires entity linker. A subsequent work made this model more generalized by having one vector per entity mentioned instead of one vector per entity, which means that when the entities are mentioned multiple times in different contexts, they will be mapped to different vectors. So it can be more expressive. So here's the paper called mention memory looks like. You can see there is a data store called mention memory, and this is incorporated to the transformers layers. And here in mention memory, every entity mention have a vector. For instance, there are 2 sequences that mention Perseus, and since they are different contexts, they are mapped to different vectors. So you can say there is some connection to KNN-LM because KNN-LM has one vector per token, whereas here we have one vector per entity mention. But this is still much more space efficient than KNN-LM because the number of entity mentions is much smaller than the number of tokens. For instance, there are 150 million mentions in Wikipedia. Okay, to summarize, there are a few papers that use entities or entity mentions as elements to retrieve from a data store. They are shown to be very effective for entity-centric tasks like question answering, and it is more space efficient. But it comes with some additional complexity, such as requiring entity detector. Okay, so far, all the papers we discussed retrieve from the external text. And this is aligned with the definition that we discussed in section 2. But you may be curious, can we use a similar approach to do something else? So we're gonna look at some of the example in the next part. So one nice thing you can do is to model long-range sequence. So imagine you have an input, but it's very long, like the entire book. It can happen for some tasks like summarization. And it's typically very hard to process this entire input because the transformers usually have a sequence length limit. So what you might want to do instead is to construct a data store using its own input and retrieve parts of it that is most relevant to the current token. So here's a figure from one of those papers called Memorizing Transformers. And this is the regular transformer-based language model. But then they have an external memory, which is constructed based on their own input instead of external text. And this memory can be incorporated to an intermediate layers of the attention layer by using KNN search. And it can efficiently operate by taking some most relevant part only and then incorporated them instead of processing the entire input. A more recent work uses a similar approach for using more advanced architecture. Here's again how the regular language model looks like. And this paper uses chunk cross-attention in the intermediate layers of transformers. This is from the retro that can process many blocks more frequently, efficiently. So how it works is it essentially constructs a data store using their own input, split into chunks, and then every chunk will be assigned a similarity score with respect to the current chunk. And they can do top k nearest neighbor search to find the most relevant part and incorporate it into the chunk cross-attention layer so that it can incorporate it to the language model. So, okay, these are some of the papers that use a similar approach, but to retrieve from a data store constructed from its own input instead of external text. Okay, that's near the end of section 3. So I'll wrap up with a summary. In this section, we talk about a few architecture designs for retrieval-based language models. We started from the most intuitive model that retrieved text chunks from a data store and concatenated as part of the input and fit into the language model. And this can be done either once or every n tokens. We see more frequent retrieval improves better performance, but can be slower. We then see how we can improve efficiency by designing an architecture that incorporates retrieval result in the intermediate layers of transformers. This comes with some additional complexity and required training, but it can be designed in a way that it is more efficient. Next, we talked about KNN-LM that retrieve tokens instead of text chunks. We saw this allow more fine-grained retrieval and can be more compute efficient. However, the data store can be very expensive in space. And afterward, we saw some of the extensions ideas, for instance, to do adaptive retrieval to improve efficiency and speed, to retrieve entities or entity dimensions instead of tokens or chunks, and to use a similar approach for long sequence input modeling. There are a few other possible extensions that I didn't discuss in this section, such as using soft adaptation instead of hard adaptation for better performance, or removing interpolation to only use KNN distribution. Please check out this paper if you're interested in. Finally, I want to mention that there are already many real-world applications that use retrieval, such as Bing Chat, GPT extension, and Perplexity. We didn't really discuss this model in this section, but if you are already familiar with them, or if you have already used them before, you might be noticed that these fall into this category of retrieving chunks and concatenating as part of the input. And as you can see, this is actually a pretty small portion of entire classes of retrieval-based language models. So I think retrieval-based language models are still largely underexplored, and we need to work on other diverse types of models that have their own pros and cons. So that's the end. And next section, we'll talk about training. And after a coffee break, we'll also talk about downstream tasks.
Okay. Hello, everyone. I'm Zexuan. So next, I would like to talk about section 4, training retrieval-based language model. So in previous section, we have talked about the architecture of retrieval-based language model. So in retrieval-based language model, we are given an input text and we feed the input text into a language model. And at the same time, we have a query and we use that query to query a retrieval index to get some retrieve index trunks. So with both the retrieve index trunk, retrieve text trunk, and as well as the language model, we are going to make a joint prediction. So next, let's consider training the retrieval-based language model. So to train the retrieval-based language model, there are two components that we want to update. So the first component is a language model. The second component is the retrieval model. So it's natural that we want to apply the backpropagation to each of these components to update them. However, there are some challenges. So the first challenge is just training the language model can be very expensive. It is especially when you have when you consider a very large language model. So the state-of-the-art language model nowadays may contain hundreds of billions of parameters. So if we want to build a retrieval-based language model based on a very large language model, we will see that if we want to update the language model, that would be very expensive. And the other challenge is on the retrieval part. So it is just because the index is too large. So we want to. So if we want to perform the backpropagation to the index or to the retrieval part, we'll find the retrieval result will actually depend on the full corpus. Well, we usually consider a very large corpus, which may contain billions of tokens. So as a result, if we want to update the retrieval part, the computation of updating the retrieval part will scale up with the size of the corpus. So more specifically, I would like to use this figure to illustrate the challenge of updating the retrieval part. So in the retrieval part, we have a retrieval index. To build that index, what we need to do is that we need to take an encoder, and we want to use this encoder to encode all the text fronts from a large corpus or data store. And once we encode them, we'll get the representation for each text front. And based on those representations, we can build an index. And because usually we'll consider a very large data store, we can actually encode a lot of text fronts. For example, we can easily encode more than 100 million text fronts. That means the index will be very large. And if you want to update the retrieval model, we can see that it's actually not hard if we just want to update the encoder. But as a result of updating the encoder, we also want to update index. However, updating the index is not easy. It's very expensive because updating the index requires us to re-encode all the text from the corpus or data store, and then rebuild the index. So re-indexing is very expensive. So we have talked about these two challenges of training retrieval-based language models. So to address these two challenges, people have proposed different training approaches for retrieval-based language models. In this tutorial, we split this training method into 4 categories. They are independent training, sequential training, and 2 categories about joint training. There are joint training with asynchronous index update and joint training with in-batch approximation. So section 4 will be 2 halves. In the first half, which is before the coffee break, we are going to talk about the first 2 categories, independent training and the sequential training. So next, let's talk about the independent training. So in independent training, what we want to do is to train 2 components independently. So there are 2 components we want to train. First, we want to train the language model, and also we want to train the retrieval model. So let's first look at how we train the language models. So training the language model is actually very straightforward, and I assume most of you are already familiar with this process. So what we want to do is to perform the backpropagation and to update the language model encoder. And the objective here we used is to minimize the negative log likelihood of the training text. So one thing to note that is nowadays the language model can be very large. It can contain hundreds of billions of parameters. So instead of training a language model from scratch by ourselves, what we can do is that we can take those pre-trained language model and use them in our retrieval-based language model. So for example, we have a pre-trained language model out there. For example, we have a GPT from OpenAI, we have a Llama from Meta. So that's about training language model. And then we're going to talk about training retrieval models. So training retrieval model is actually a very fundamental problem in field of NLP and information retrieval. And people have been proposing many different methods over the years. And here in this tutorial, we are just cover a couple of them that people have been widely using. So one type of the retrieval model is the sparse retrieval model. For example, TF-IDF or BM25. So in sparse retrieval model, what we do is that we map a taxon into a sparse vector representation. So the sparse vector representations are usually very large and it contains many dimensions, but most of the dimensions will have the value of 0. So that's why it's called sparse vectors. Once we have the sparse vector representations, we're going to define a similarity function based on some heuristic to measure the lexical overlap between these two trunks. So because here the similarity function is predefined based on some heuristic, so there is actually no training needed. And in recent years, people have been using dense retrieval models. And among those dense retrieval models, one popular model is called DPR, or dense passage retrieval. So this model uses a bird size encoder to map a taxon into a dense vector representations. And once we have the dense vector representations, the similarity between two taxons can be defined as the inner product of the corresponding dense vector representations. And during the inference, it will be straightforward. In the inference, we are given a corpus. So we first use the encoder to encode all the taxons and map them to a dense vector representations. So once we have this set of dense vector representation, we can build a retrieval index based on that. Then once we have a query, similarly, we use the encoder to get the query representation. And we use that query representation to retrieve the top K maximum inner product value. And we are just going to use the top K item with the maximum inner product value as our retrieval result. Then our next question is, how can we train the dense retrieval models? So to train the dense retrieval model, here we should, to train the DPR, we are going to use this training objective, where we are given a query and we compute a probability distribution over some passages or text trunks. And the objective here is to maximize the likelihood of the gold passage that we want to retrieve given this query. And this objective is actually a case of contrastive learning. So very briefly speaking here, in contrastive learning, we are given some data sample that we know that they should be similar and their corresponding representation should be close to each other. And we call those data sample positives. And at the same time, we are also given some dissimilar data sample, and we want the representation to be pushed away, and we call them negatives. And in this specific example, the positive will be naturally the gold passage that is corresponding to the query. And if we consider the negatives, so ideally what we actually want to consider is all the negative passages that come from a large corpus. However, that will be very expensive. So what we actually do here is to use a technique called training with in-batch negatives. So the idea here is that instead of considering all the negatives coming from a large corpus, here we only consider the negative passages from the current training batch. So here is an example. Suppose that we have a training batch which contains a set of query and the corresponding gold passage pairs. And for the positive, it's very natural that we take the gold passage and as the positive. And for the negative, instead of taking the negative from the full corpus, so here we only consider the negative in the same training batch. So specifically, what we consider here is we regard all other passages as the negatives in this equation. So the good thing of doing this is that we can get those negative representation for free because they are in the same training batch and we need to compute their representation anyway. And more importantly, because those representations are computed on the fly, we can actually perform the backpropagation through all these in-batch negatives. Okay, so this is the training about the DPR model. And when we train the DPR model, we assume that we have already annotated the query and the corresponding gold passage. And recently, people have been proposing training dense retrieval models in an unsupervised setting. And one paper we would like to quickly mention is this controller model. So when you want to train a dense retrieval model in an unsupervised setting, another key problem is that you don't have the annotation for you to select the positives. So in this paper, they propose to use independent cropping method to get the positive signals. So what we do here is very simple. We take one document and we just do 2 times random copying for that document. Then we get 2 pieces of text and we just regard them as the positive. So this paper have shown that with this training signal, you can train a very powerful dense retrieval model in an unsupervised setting. Okay, so that's about the training technique of retrieval model. And then let's review some concrete example of retrieval-based language model that are based on 2 components trained independently. So the first paper we're going to talk about is the retrieval in context approach, which we have a talk about the architecture in last section. So in this model, we are given an input X, and we use that input to retrieve some relevant text, and we just concatenate the retrieved text with the input text to make the joint prediction. And what is key here is this model is based on 2 components trained independently. So that means that we can plug in any off-the-shelf retrieval model or language model here. So for example, for the retrieval model, we can use BM25 or we can use DPR. For the language model, we can use GPT or Llama. And this paper also showed that if you simply have a better retrieval model or you just have a better base language model, you can improve the final performance of your retrieval-based language model. So that means in this setup, each component can be improved separately. And the improvement can be easily transferred to the final performance of your retrieval-based language model. Okay, so the second example in this category is the k-nearest neighbor language model, or KNLM. We have talked about how we do the inference in last section. So basically, we are going to build a token level data store, and we are going to do a token level retrieval. And then our final prediction is based on the interpolation of the language model part and the retrieval part. And what's the key here is for the retrieval part, we are going to use the same encoder as the encoder we used in the language model. So that means that we will not have any training part that is specialized to the retrieval. So for the training, what we do is just to train a normal language model. And we just modify the inference to reuse the encoder we trained from the language model. So because in this case, there's no any training specialized to the retrieval part, so we put this work in this category that we train these two components independently. Okay, so this is about our first category, independent training. So the good thing of independent training is that those approaches can work with off-the-shelf model. That means we can take a very strong off-the-shelf model and directly use that. There's no extra training required. And also we have seen that each component can be improved independently. So obviously there are some limitations for the independent training approach. For example, the language model are not trained to leverage the retrieval result, and the retrieval models are not optimized for the language modeling task or a specific domain. So this is about the independent training. And next, I would like to talk about the second category of the training method, which is sequential training. So the sequential training basically means that here we want to train two components, and we just train one component first and independently, and then we just fix that component. And at the second stage, we're going to train the other component, and we train the other component with an objective that depends on the first component that we train independently. So there are actually two cases of sequential training. In the first case, we first train the retrieval model, and we fix this retrieval model, and we train a language model after that. And in the second case, we first train a language model, and we fix this language model. And usually, this language model we consider is very large, and it will be very expensive to update that. So we fix this language model, and then we train the retrieval model to make sure that the retrieval model can provide useful text for this language model. So let's first talk about our the first case in the sequential training. So as I said, in the first case of the sequential training, we first train the retrieval model, and then we train the language model to make sure the language model can effectively leverage the retrieval result. So as shown in this figure, we're going to update the language model with backpropagation technique. And we are also going to apply a stop gradient operation on the retrieval part to make sure we fix that part. So the first paper we talk about in this category is Rachel. So in Rachel, we are given input text, and we split this text into multiple text trunks here, X1, X2, X3. And we use this text trunk to retrieve some other text trunks. And then we fit them into a language model encoder. Then we get the reputation for those retrieved texts, E1, E2, E3. And the final prediction of the Rachel model is made by jointly considered E1, E2, E3, as well as the input text X1, X2, X3. And we have highlighted the effectiveness of the Rachel model. So the key thing of the Rachel model is that the index that Rachel model used is extremely large. So during training, we're going to consider 600 billion tokens, and during inference, we consider 1.8 trillion tokens. So that means updating the index will be extremely expensive. So during training, it will be infeasible if we want to update the index. So then let's consider training the Rachel model. So to train the Rachel model, naturally we want to apply the gradient descent or backpropagation to update each component of this model. And as we discussed, the index is very large, so updating the index will be extremely expensive. So here we are going to apply the idea of sequential training here. So what we do is very simple. So before the training starts, we are going to use the retrieval encoder to encode all the text chunks that we considered. And we build the index and we just fix them. And then we'll just apply the backpropagation to update all other components in the retrieval model. So you can see in this figure, we have a stop gradient operation on the retrieval part. That means we will not update that part. Okay, that's the first case of the sequential training. And then we're going to talk about the second case. In the second case of the sequential training, we first train a language model, and then we're going to fix that. And here we usually consider a very large language model, which means that it will be very expensive if we want to update that. Or we even consider a black box language model, which means that we will not have the access to update the language model. And at second stage, we are going to update our retrieval model with some supervision from the language modeling part. So the paper we're going to talk about as an example is a replug paper. So this replug model, similar to other retrieval-based language model, some other retrieval-based language model, given an input text, we're going to first retrieve some relevant document or relevant text chunks from a retrieve index. And then we're going to refine the prediction by looking at those retrieved texts. So specifically, we're going to process each of these retrieved texts, and we do an ensemble prediction at output layer. So this replug paper, this replug model can work with any two off-the-shelf retrieval model or the language model. And in this case, it's actually should fall into the case of independent training. So more importantly, this paper proposed another approach called replug LSR, or replug language model supervised retrieval. So here we are going to apply the sequential training to train the model. So what we do here is during training, we retrieve some text chunks, and we can know that if a text chunk can contribute, how much if a text chunk can contribute to our final prediction. So we can know that some text chunk can contribute more, some text chunk cannot contribute more. And then we're going to update the retrieval. So the idea here is to encourage the retrieval to retrieve those text chunks that can help the language model to make the better prediction. So with this technique, we are able to update the retrieval model with the supervision from the language model. And one issue here is that when we update the retrieval model, we need to handle a large index. And this model uses a technique called asynchronous update, which we will talk about it very soon in the second half of this section. Okay, so then let's look at some result of this replug model. So first, this result shows the BPP value, which is lower the better. And here we have different models with different size. So if we use the replug model with just the off-the-shelf dense retrieval model contriver, and in this case, it's actually the case of independent training, we can see that we can get improvement across all the cases. And if we further consider the sequential training technique, where we are going to update the contriver model with the language model supervision, we can see that we can further improve the result across all the cases. Okay, so this is about the sequential training. And the good thing about sequential training is still we can make the approach work with some off-the-shelf strong component. Either we can use a very large index or very powerful language model. And because at the second stage of the sequential training, we already consider some joint objective to train the model. So either the language models are trained to leverage the retrieval result, or the retrieval model are trained to provide the text that can help the language model the most. However, we can see that still one component of the retrieval-based language model is still fixed and not optimized. And then we are going to talk about address this issue in our next half. So then we will have a coffee break. I guess before the coffee break, we will have the Q&A session. Yeah, feel free to raise questions.
So it's a coffee break time, so please feel free to leave and come back at 4 p.m. But we'll stay for 5 or 10 minutes. So if you have questions, please, yeah, go ahead. Yeah.
How can we test? I don't know. How can we check that? Why is this? Sorry. Oh, maybe it's okay.
I think it's. What?
69.
Okay. Is it?
Okay. Okay. I think we can get started on time. Okay, so hello everyone, I'm Zexuan. Welcome to our tutorial. Our tutorial is about retrieval-based language model. And right now we are on section 4, training retrieval-based language model. So as a recap, in the first half of this section, we have talked about why training retrieval-based language model is challenging. And we talk about there are two challenges. One is on the language model part, one is on the retrieval part. And people have proposed different training approaches to address these two challenges. And before the break, we have talked about independent training and sequential training. And next, in the second half of this section, I would like to talk about joint training. So there are two categories in joint training. There are joint training with asynchronous index update and joint training with in-batch approximation. So in the joint training, we are going to train our language model and retrieval model jointly at the same time. So when we train our retrieval model, one key challenge comes. That is, in the retrieval model, we have a retrieve index. And during the pre-training, during the joint training, we are going to update the retrieving encoder. And as the result of updating the retrieve encoder, we also want to update the index. However, because the index is built based on the full corpus, and if we want to update the index, what we want to do is to re-encode all the text chunks from the data store using the up-to-date encoder, and then rebuild the index. So that would be very expensive, and that's a key challenge when we consider updating the retrieval in our joint training methods. Okay, so let's take a look at how people address these challenges. So the first category we talk about is joint training with asynchronous index update. So what does this approach mean? Is that it's a joint training approach where we are going to train the retrieval model and the language model jointly. So we want to update both the retrieval model and language model. And to deal with the super large index during training, what we do here is that we are going to consider a very large full index. But what's the key here is that we allow the index to be still. And the ideal case is that every time we update the encoder, we want to rebuild the index. So here we allow the index to be still, and we're going to use the still index for a while and only rebuild the index every T training steps. So more specifically, in the retrieval model, we have an encoder and an index, and the index is very large. And every time we update the encoder, the index will be still. So you can see here, the encoder is updated, but if we don't update the index is outdated. So the idea of asynchronous index update is that we allow us to use this stale index during training. And when we are going to update that, so every T training steps, we are going to update the index, meaning that we're going to re-encode all the text chunks and rebuild the index using the up-to-date encoder. So that's the idea of asynchronous index update. Okay, let's look at some example that train the retrieval-based language model based on the idea of asynchronous index update. So the first paper we talk about is RHYME. So in last section, in section 3, we talk about the architecture of the RHYME model. In RHYME, we're given input text X, and we retrieve some text chunks from a retrieve index. So then we concatenate the retrieve text with the input text to make a joint prediction. So during training, what we want to optimize is to maximize the likelihood of the gold training text. Where in this objective, the retrieve text serves as a latent variable, and we have two models to update. One is the retrieval model. Here is the P of Z given X. Another is the language model, which is P of Y given X and Z, where Z serves as a latent variable here. So if we perform the backpropagation, we'll find that it's actually easy to get updated for those encoder part. So we can update the encoder in the language model and also the encoder of the retrieval model. However, the index will become stale. So the idea of using asynchronous index update is that we're going to update the encoder every training step. So here we can see that the parameter of to encoder is up to date, and then we're going to use the stale index for a while and only update the index every T steps. So that means between two flashes during training, we're just going to use the stale index to compute our training objective. So here you can see the top K retrieve tags are actually based on the stale index. And here it's equivalent that we use the old retrieved result as an approximation to the up-to-date retrieved result. So this is the training techniques of RHYME. It is based on the key idea of doing asynchronous index update. And one key design choice of asynchronous index update is how often should we update the retrieval index. And here we have a trade-off here. So if we update the retrieval index too frequently, the training will be very expensive. So the extreme case is that we every time we update the encoder and we update the index, that will be extremely expensive. And on the other hand, if we update the index very slowly, the index will be too outdated or too stale, and it will actually hurt the performance of the retrieval-based language model we are going to train. So in the RAM paper, they update the index every 520 steps. And they have the evaluation study showing that if we update the index much more slower here, if we update the index 30 times slower, the performance of the retrieval-based language model will be much worse. Okay, so that's the first paper we are going to talk about, and then we are going to talk about this Atlas model, which is also trained with the similar idea of asynchronous index update. So different from the RAM model, the Atlas model is a retrieval-based encoder-decoder model, which is based on T5, while the RAM model is an encoder-only model based on the BERT model. And similarly, in the RAM model, in the Atlas model, what we're going to do is to give an input text, we retrieve some relevant document or relevant text chunks, and then we are going to process each document independently using a technique called fusion encoder. And very quickly, fusion encoder is an approach that allows us to use the sequence-to-sequence model or encoder-decoder model that to process multiple documents at the same time on the encoder side, and to fuse the information on the decoder side to make a joint prediction. And thirdly, Atlas is a pre-trained language model that can be adapted to a lot of downstream tasks, which we'll talk about very soon in section 5. Okay, then let's look at some training techniques that Atlas use. So different from the RAM model, where we use the retrieve text as the latent variable in our training objective. Here, Atlas try to use the language model as a guidance to guide the training of the retrieval model. So here, we want to align two things. The first thing is that how likely a text chunk can be retrieved by the retrieval model. And we're going to align this to how much a text chunk can improve the language model on the perplexity. So intuitively, we are going to encourage the retrieval model to retrieve those text chunks that can improve the perplexity. So concretely, we are going to use the KL divergence to measure the alignment and minimize the objective based on this KL divergence. And we call this method perplexity distillation. So with this training objective, we are going to update our retrieval model. So when we update the retrieval model, we still have this key issue that we need to handle a very large index. So here, the similar idea applies. We are going to use asynchronous index update. So that means we want to update the index every t steps, and we will need to carefully choose the value of t. And in the experiment of Atlas, they trained the model on the Wikipedia, and it will cost 30% training overhead after carefully design the value of t. And we can see that the Wikipedia is not a super large corpus, and if we consider training the model on an even larger corpus, we can get even more training overhead. So how can we get rid of this? Then here comes the second category of joint training. That is joint training with in-batch approximation. So the idea of joint training with in-batch approximation is that in this type of approach, we are going to train the retrieval model and the language model jointly. And then because the full index is very hard to handle during the training. So unlike the asynchronous index update, where we handle a stale full index. So here we are not going to consider the full index during training. So what we do is to use the in-batch approximation, which is approximation to the full index during training. And all the computation will be based on this in-batch approximation. And it will allow us to do the backpropagation and to update the retrieval model. So more specifically, what is the in-batch approximation meaning? So during the training, we are going to update the encoder, and we have talked about this, updating the encoder. After updating the encoder, we want to update the index. And if we want to consider the full index, so re-indexing will be very expensive. So it will be not feasible to update the full index during training. And the idea of using in-batch approximation is that we are not going to consider the full index during training. And what we do is that we are going to always take the up-to-date encoder to build a index based on the current training batch. So every training step, we have a training batch, and we'll take the current up-to-date encoder, build an index based on that. So the index here is called in-batch index. And all the computations, including the training loss and also the backpropagation, will based on this in-batch index. So although this in-batch index is much smaller compared to the full index, usually the in-batch index only contains 10,000 elements. Although it's very small, we're going to apply some techniques to make sure the in-batch index is actually a good approximation to the full index. Okay, so in this category, the first paper we're going to talk about is the TRIME model, training with in-batch memory. So this model is very similar to KNLM doing inference, where we define the data store as a set of tactron and the corresponding next token pairs, similar to K-nearest neighbor language model. And doing inference, we are given an input text X, and we feed this X into the encoder, and we are going to do an interpolation at the output layer to get a final prediction. So specifically, what we do here is we align the output representation of the input with some token representation. And also, we align the input tactrons with all the tactrons in the data store or in the index that share the same X token. And doing inference, we're going to consider a very large data store. So here we need to apply a K-nearest neighbor search. So if we dive into this objective we used in TRIME, we'll find that it is essentially a case of contrastive learning, where we have some chunks. We know that they should be similar, and we want their representation to be close. And essentially, in the case of TRIME, if two chunks have the same next token, they are essentially positive chunks, and we want to train the model to make them together. And otherwise, they are negative. And the problem of using this training objective to train the model is that it's still the index or the data store is super large. It's very hard to handle during training. So to train the TRIME model, what we do is based on the in-batch approximation. So the key idea is we build a temporary index from the same training batch on the fly. So this is the objective we're going to use during training. So compared to the equation we just saw during inference, the only difference is here we are not going to consider the full data store or full index, but we are going to consider the in-batch approximation, which is computed on the fly. So because we compute this loss based on the in-batch index, so all the representation are computed on the fly, so we can perform the backpropagation through all the representation in this data store. Okay, So next, let's compare the full index and the in-batch index to have a better sense of how the in-batch index look like. So during the inference, we are going to use the full index. And in this case of the TRIME or KNLM, the index is token level. So the size of full index will be equal to the size of full corpus, which is very large. During training, instead of considering the full index, we consider the in-batch index, which is built on the training batch, and it is much smaller, and all the representation are computed on the fly. And we use it as a proxy to the full index during the training. And then our next question is that how can we make sure our in-batch index is actually a good proxy to the full index during training? In other words, how can we batch the training data so that we can have a good in-batch example to build the temporary index? So the TRIME paper proposed a data batching strategy. So the idea here is simple. So instead of random batching text trunks to get a training batch, so here we are going to batch the similar text trunks to get the training batch. And specifically here, we are going to use BM25 score to find those similar text trunks. And if two text trunks have a high BM25 score, it basically means that they have a high lexile overlap. That means that we will have more positive pairs within the training batch. That means we get more training signal. Okay, that's the training technique of the TRIME model. Let's look at some result of this model. So we compare TRIME with two baseline. One is the vanilla transformer, the other is KNLM. So first, we can see that the KNLM is better than the vanilla transformer. And then compare the TRIME model with the KNLM. We can see that we can further improve the perplexity by about 1 point. And this improvement comes from the joint training of the retrieval and the language model part. Okay, so that's the first paper we talk about. And then we're going to talk about a model called NPM, non-parametric mask language models. And this model is trained with a similar idea of using in-batch approximation. So compare NPM with the TRIME model, there are some key differences. So first, this model is a mask language model pre-trained on more data. Second, it is a phrase level language model instead of a token level language model. And third, the prediction of NPM is made purely based on the retrieval part or the non-parametric part. So that's why this model is called non-parametric language model. So we'll not dive into the architecture of this model, but we'll focus on the training technique. So to train the NPM model, we'll also use the in-batch approximation idea. The key challenge here is still how to approximate the full index and how to get the training signals. So this paper uses an in-batch approximation with send document batching. So what does that mean is that instead of using BM25 to batch the data, we just sample the sequences from the same documents. The reason we do not use BM25 here is that BM25 would be very inefficient for a very large corpus. And once we sample the sequences, we just identify co-occurring spans, and we use those co-occurring spans as positives and others as negatives. So that's the training techniques that the NPM used. And one limitation of this TRIME model and NPM model is that here the retrieval models are only trained to leverage the lexical information. That is because when we define the positive and negatives, we only use the lexical clue. For example, we define the positive based on the co-occurring tokens or spans. So the question is, can we do more than that? So a very recent paper proposed an idea that can help us to better define the positive and negative. So the model here, it will be very different, but we're going to only focus on their definition of the positive and negative. So given a text trunk, we want to find the positive and negative. So what we do is that we find some reference trunk, and based on this reference trunk, we get some score, which is a reference score. It is basically the contribution of this reference trunk. If we use that to make the joint prediction on the next token. So if another trunk can make a better contribution than this reference trunk, we regard it as positive. Otherwise, it is negative. Okay, so this is all about the joint training. So the good thing of the joint training is, of course, we find a way to train the retrieval-based language model in an end-to-end way, and we can get good performance. And the shortcoming of the existing joint training is that by using those techniques, the training will become more complicated, because we need to either use the asynchronous update. It will introduce some training overhead, or we need to design some special data batching method. And still, although we have some approaches to train the model in an end-to-end way, because we do some different levels of approximation, so the training and testing discrepancy still exists. Okay, this is section 4. To summarize, so we talk about different training methods, and there are 4 categories: independent training, sequential training, and the joint training with asynchronous index update, joint training with in-batch approximation. And we have talked about the pros and cons of each category. So next, in section 5, we're going to look at how those retrieval-based language model can perform on downstream tasks. And I will let our colleague to take over. Thank you.
Hey, hello everyone. So my name is Akali Asai, and in this section, I will talk about retrieval-based language model adaptations for different downstream tasks. So in section 3 and 4, we have been talking about architecture and training strategies of retrieval-based language models in the context of language modeling, where given an input sentence, the model predicts the best continuation. When it comes to downstream adaptation, the input and output format can be quite diverse. For example, if the downstream task is an open domain QA, then the input is a question and the model outputs the answer. Or if the task is fact verification, then given a factual statement, the model identifies whether this statement is actually correct or not. So as we discussed in previous sections, retrieval-based language models initially developed and evaluated in knowledge-intensive tasks, including question answering, fact verifications, and knowledge-grounded dialogue. And nowadays, retrieval-based language models have been used in many more general NLP tasks. And those tasks include summarization or like code generation, which generate more longer form generations, or NLI or sentiment analysis, where a fixed set of classification or like choices are pre-given. So in this section, I will talk about some two important questions for downstream adaptations. So how can we adapt a retrieval-based language model for different target tasks? And when should we actually use a retrieval-based language model? So for the first part, I will talk about multiple papers which are focused on how to adapt. And in particular, I will talk about 3 widely used adaptation methods: fine-tuning, reinforcement learning, and prompting. So fine-tuning or fine-tuning plus reinforcement learning involves parameter update of language model and or retrieval component using task data. Recently, we found that prompting a frozen large language model with retrieval knowledge can be actually quite effective in many different tasks. And this doesn't require any training in task data and can be pretty simple extension. And we can extend this approach to many different tasks. And in this part, I will talk about the pros and cons of different adaptation methods and also answer more technical questions. For example, should we update both retrieval and language model component, or where we should incorporate those retrieval knowledge in inference pipeline, or how to prompt language model. Also, another key aspect when it comes to downstream adaptation is what kind of data store we should use. So in open domain QA or knowledge intensive tasks, using Wikipedia or unlabeled corpora, for example, CCNet, can be quite helpful. While many papers also found that if we use training data or like related example as data store, it can be also helpful for some tasks like machine translation. So I will also briefly discuss this aspect in this part. After the first part, I will talk about second important research question, when to use a retrieval-based language model. So we discussed some key effectiveness of retrieval-based language model in introduction. And in this part, I will focus on 4 of those effectiveness. Now I would like to briefly recap those different effectiveness. So large language models have shown to be quite competitive in many different tasks, but we also found that those models can hallucinate a lot or struggle in knowledge-intensive tasks. For example, if we ask a simple question, is Toronto really cold during winter? Then language model can easily answer. Well, if we ask more specific question, where is Toronto Zoo located? Then the language model answer can be incorrect because it is challenging to memorize everything in their own parameters. In retrieval-based language models, we can retrieve helpful document from data store and incorporate them during inference time so that we can avoid those errors. Also, language models are typically pre-trained corpus, which is collected at certain timestamp, and the parametric knowledge is fixed at this point. But the world is constantly changing, so we have to keep up with those state-of-the-art knowledge. So for example, if I ask a question, what is the population of Toronto metropolitan area in 2023, then even ChatGPT can generate incorrect answers based on their 2021 knowledge. In retrieval-based language model, we can simply swap data source with a newer data source and update those parametric update the model's knowledge. Many papers also show that retrieval-based language model has a much better verifiability or attributions by help human to verify whether the generations are actually correct or supported by evidence. Also, many papers found that retrieval-based language model can be quite competitive in some tasks and even outperform much bigger large language models. So first, I'd like to discuss how can we adapt a retrieval-based language model for a specific downstream task. And I would like to start talking about the paper using fine-tuning for downstream task adaptations. So fine-tuning involves parameter update of language model or retrieval language model and or retrieval component using the task data. And actually many papers we discussed in section 4 conduct fine-tuning using task data, for example, open domain QA dataset to get the best performance on those different downstream tasks. And one challenge is that, as we discussed in section 4, the training of retrieval-based language model can be quite expensive. So many papers explore different strategies, for example, independent training or asynchronous update. And so now I would like to revisit the Atlas paper, which we discussed in section 4. So in Atlas, given the input X, the model first encode query using query encoder and then retrieve documents from index, which is encoded by document encoder. Then given the retrieved document Z, the model takes input X and the retrieved document Z to generate the final output. And in Atlas paper, they fine-tune those language model and also in the retrieval component using few shot task data from different tasks, for example, like question answering. One challenge is this training can be quite expensive if we want to update the index during training time. And so in this paper, they explored different approaches to conduct such efficient fine-tuning of retrieval-based language model. So one simple approach is just fix retrieval component with the pre-trained state and only update language model component. So in this way, we only update the language model parameter during fine-tuning, while like we completely fix the document encoders and also index. As we discussed in section 4, this type of approach can be suboptimal. And so they also explore different approaches to improve the performance. So one approach is query-side fine-tuning, which they still update query encoder, but keep the document encoder and index as a pre-trained state. So by doing that, we don't need to update the index or document encoder during training. And so we can use the same index for different tasks, and we don't have computational overhead to compute the index during training. And the experiment shows that if we just fix retrieval component for different downstream tasks, then we see large performance deterioration from standard fine-tuning. Here, standard fine-tuning means asynchronous update, as we discussed in section 4. And they actually found that query-side fine-tuning, although it's quite efficient, is actually quite competitive, and it matches or outperforms full fine-tune approach. Also, another interesting finding from Atlas paper is that they explored different training setup, few shot, full shot, and also transfer. So few shot is their main setup, and they only use small number of training data in each target task. For example, like just 60, for example, and they fine-tune the model using the strategy I discussed. Another approach is, another setup is full shot training, where they use all of the training data in the target task. For example, if we evaluate the model, if we train the model for natural questions, which is an open domain question answering data set, we have a large number of training data. So they use the full training data during training time. But not all of the tasks have a large number of training data. For example, MMLU, multiple choice question answering data set across domain, doesn't have any dedicated training data set. So they also explored another setup, transfer setup, where they train the model using similar data set, for example, MC test to MMLU. And they found that on open domain QA tasks, for example, natural questions or trivia QA, Atlas largely outperform other large language model, even in future. And they also found that if they train the model using full training data, then they can get large performance improvement and outperform all of the state-of-the-art method at that time. On the other hand, on MMLU, Atlas Fusion largely underperform Chinchilla or GPT-4. This indicates that there is still room for improvement for diverse task adaptations. They actually found that transferring from related dataset gives large performance improvement, and they can match much larger large language models such as Chinchilla. So Atlas, or many papers we discussed in prior sections, fine-tune retrieval-based language model for downstream tasks, including question answering or knowledge-intensive tasks, and shows really strong performance. And one key finding is that fine-tuning a retrieval component is quite effective to get the best performance. So now I would like to talk about second approach involving parameter updates. So recently we found that training large language model using reinforcement learning can give us better alignment with user preference. And for example, like Instruct GPT have shown quite effective performance and flexibility in many different scenarios. And one open question is that how should we conduct such retrieval-based, such reinforcement learning with human feedback for retrieval-based language model? So this Go4Site paper and also concurrent work with GPT explores the effectiveness of reinforcement learning for such retrieval-based language model adaptations. So in Go4Site, they trained the model to generate answer with verified quotes. So in question answering, typically we only generate answer to a question. Well, in this work, they fine-tuned 280 billion GOFA model to generate answer with verified codes, which by extracting and generate the code from retrieved documents. So how it works? So first of all, unlike Atlas, GOFA site uses off-the-shelf Google search system as data store, so they don't fine-tune retrieval component at all. And first they retrieve helpful documents from Google search, and then the language model takes the input question X and retrieve document Z, and then generate output Y, which consists of answer and also verified codes. And during training, one important thing is that we don't have large-scale training data set, including answer and also verified code. So they actually create a large-scale training data by prompting language model and then filter training data by human. And once they collect training data, they conduct supervised fine-tuning and only update language model. They explore the effectiveness of reinforcement learning with human feedback in this work, which is similar to InstructGPT. So what they did is that they collect the human preference data, given two different outputs to the same input X, and then train reward model. And after that, they use this reward model for reinforcement learning or use reward model for better sampling. And I will skip the detail of the reinforcement learning here, but I would like to briefly talk about how they collect this preference data to build a better retrieval-based language model. So in InstructGPT or general NLP model training, we typically ask human to give overall preference data. In GOFA side, they ask human raters to give preference based on two specific aspects, which is crucial in information seeking scenario. So the first one is if the answer is actually plausible to the input, and the second one is if the answer is supported by accompanying evidence. So if the language model generates an answer that sounds very reasonable or plausible, but is not supported by the evidence, for example, the answer is hallucinating or the evidence is not really helpful, then those outputs shouldn't be preferred. Based on this criterion, they collected 30,000 human preference data and then trained reward model. The experimental results shows that this reinforcement learning is quite effective to make retrieval-based language model better aligned with human preference. And as you can see, the blue bar is indicating the fine-tuned model performance, and the green bar indicates the reinforcement learning performance. And there's a huge performance improvement by conducting reinforcement learning with human feedback. Also, they found that using this reward model to sample better output gives large performance improvement from using top one generation from fine-tuned models. So far, we discussed two papers conducting fine-tuning and also reinforcement learning. So in summary, there are several benefits of fine-tuning. For example, fine-tuned models, fine-tuning is more customizable and also show really competitive performance, especially if we have more data. At the same time, we have to train the model, which can be quite expensive. GOFA side shows the benefit of reinforcement learning on the top of fine-tuning. This helps us to build better aligned models, but at the same time, it requires additional training data corrections. So one naive question is, what if we cannot train large language models for downstream tasks? For example, we don't have enough computational resources to training model, or we want to use a state-of-the-art language model API, such as GPT-4. And in those cases, we cannot directly update language model parameters. So now I would like to briefly talk about a few papers about this prompting approach for retrieval-based language model. So prompting has shown to be quite effective in many different NLP tasks. And essentially, in prompting, instead of updating the model parameters, language model parameters using training data, we format training instances in certain way, and then we prompt language model with this demonstration and also test instance. And the language model predicts the best continuation, which can be the expected output here. And it doesn't require any training or parameter update, but still many papers show that this approach can get real competitive performance. Retrieval-based prompting simply extends this prompting approach using retrieval component. So in retrieval-based prompting, we retrieve documents and then we incorporate retrieved documents in this prompting pipeline. So how it works? So there are one important design choices here. We discussed different architecture in section 3, and there are many ways to incorporate retrieved knowledge. Here, we assume that we use a frozen language model and we don't have access to the language model itself. So in retrieval-based prompting, we typically conduct input space incorporation or output space interpolation. And first, I would like to talk about output space incorporation in output space interpolation, which extends KNN language model for downstream tasks. And I would like to introduce KNN prompt paper, which extend KNN language model with fuzzy verbalizer for zero or few shot classification task. And so KNN prompt is based on KNN language model, which we covered in section 3. And I would like to briefly recap KNN language model. So KNN language model predicts the next token and also predicts the next token using KNN model, which retrieves similar context in data store. And then KNN language model interpret output token probability. So one challenge of applying this KNN LM for classification task is that the KNN token distributions are quite sparse. For example, if we assign the token grade to positive sentiment and the token terrible to negative sentiment, then the final decision should be negative because the terrible has higher probability. But as you can see, both great and good can be positive sentiment. So those two tokens should be considered. So KNN prompt address these issues by introducing fuzzy verbalizer, which maps token probability to target class levels. So basically the KNN prompt expands a mapping function using globe embedding and also ConceptNet. And they found that this adaptation for target task gives large performance improvement from KNN language model, especially on sentiment analysis and topic classification task. And it should be noted that KNN prompt shows the effectiveness of retrieval-based language model in general NLU tasks such as sentiment analysis, topic classification, or entailment. This indicates that even though the downstream tasks are not apparently knowledge-intensive tasks, still you have a good chance of getting performance improvement by using retrieval-based approach. So now I would like to talk about input space incorporation, which incorporate retrievable documents in input space of large language model. So this approach, which we also covered in section 2, is it's quite simple, but very effective in many different tasks. So this approach, retrieval in context, basically retrieve helpful document from data store using retrieval, and then we put these retrievable documents before or after the original input X. And then we prompt language model using this input X and also retrieve document Z. And many papers show that this simple extension gives large performance improvement from the vanilla prompting. Now I would like to revisit the Replug paper, which we discussed in section 3 and 4. So in Replug, they extend this retrieval in context approach to consider multiple documents at the same time. So first, Replug retrieves top 10 documents, and then they process those different documents in parallel. So first, for example, here we have input X and we process the first document, and the model assigns the highest probability to the word token. And the second, when we prompt language model using this second paragraph, then language model can assign higher probability to Ottawa. In the plugs, they aggregate this token probability and determines the final predictions. So here, when we aggregate the token probability of those two documents, then Toronto has higher probability. So the final answer will be determined as Toronto. And the Retrieval paper shows that they can achieve large performance improvement from the base Codex model on both MMLU and also natural questions. So one night question is, which one is better, Atlas or Retrieval? Atlas is fine-tuning model and Retrieval is prompting. So the answer is depending on the task and also your setup. So for example, in future setup, Retrieval outperform Atlas in both MMLU and natural questions, but larger performance difference happens in MMLU. This is because the base language model Atlas using is Codex, which is much more competitive in this MMLU task than Atlas. On the other hand, if we use more training data, like full training setup or transfer setup of Atlas, then Atlas actually outperforms Retrieval. So in summary, retrieval-based prompting has many different benefits. It doesn't require any training, but still it can yield really strong performance across many different tasks. As the approach is quite simple, so you can simply extend this approach to your downstream tasks. On the other hand, it's harder to control and has higher performance variance. And if you have more training data, then it can underperform the full fine-tuned models using all of the training data. So far we discussed 4 papers using Wikipedia or unlabeled computer or Google search as data store. As I discussed at the beginning, there are many different data stores that can be useful in many different tasks. So before wrapping up this part, I'd like to briefly introduce doc prompting. This is a new paper trying to improve the code generation, natural language to code generation model by retrieving helpful code documentations. So how it works is that given the natural language description of the code, they first retrieve related documentations, and then they generate a model to generate based on this input X and also the retrieved documentation. For example, here the input is generate HTML with Python syntax. And so the model find documents about Python syntax highlighter or HTML formatter. And then the generator model generate condition on those documentations. So how it works is first doc prompting retrieve those documentations using either lexical retrieval model or trained retrieval model. And then they explored both fine-tuning approach, so fine-tuning smaller code T5 or prompting code much larger code X. And those models are trained or prompted to generate code given the input X and also retrieve documentations. And in both strategies, they show large gain by doc prompting. And they also see a large performance improvement in code T5. And this is potentially because code T5 is much smaller and it can be really difficult to memorize complex syntax using such smaller number of parameters. But at the same time, doc prompting paper shows that there's a huge room for improvement in the retrieval component too. So they have a really interesting ablation of doc prompting using the retrieved documents, the model retrieved by the retrieved component, or the doc prompting with Oracle document. And as you can see, the green bar using Oracle document shows much higher performance than the original doc prompting method. This indicated that the original doc prompting method might be restricted by the failure of retrieval. And actually, like adapting retrieval models for such like diverse downstream domains, or like zero-shot retrieval is an active area in information retrieval and NLP right now. So in this part, I covered 5 different papers, which uses different, for different downstream tasks, adaptation method, and data stores. Wrapping up, so to make your retrieval-based language model adapt to different downstream tasks, you can either do prompting or fine-tuning, or fine-tuning plus reinforcement learning. Retrieval-based prompting is quite easy and simple, and it doesn't require training, but also has higher performance variance, and you have to be carefully prompt language models. Fine-tuning requires training, so it can be expensive, but it has less variance, and it can be more competitive if we have more training data. Also, when it comes to downstream adaptation, it is quite important to train a retrieval model or like build a task-specific retrieval model for downstream tasks. And data store can be diverse. And I will briefly talk about extension of retrieval-based language model in section 6, where data store can be even like different languages or different modality. And it is still challenging to build a general purpose retrieval model for such diverse use cases. So now I'd like to briefly talk about when we should use a retrieval-based language model. So in this part, I will focus on 4 different effectiveness or like use cases of retrieval-based language models. And we talk about different results from different papers to summarize when retrieval-based language models can be quite effective. So the first key effectiveness is the performance in long tail or knowledge intensive setup. So many recent papers show that large language model can often struggle in long tail or less frequent entities. In this paper, they show that the large language model performance on open domain QA can be much worse when the question is talking about less popular entities. And as you can see, there's a clear upward trend from the left side and right side. Another concurrent paper shows that this struggle in long tail cannot be resolved by simply scaling language models. Here, the red line shows the model performance on more popular entities, and the blue line shows the model performance on less popular entities. And as you can see, the model performance on more popular entities can get better as the model size increases, while the model performance on less popular entities remain low, even if we scale model size from 1.3 billion to 175 billion. Retrieval-based language models, on the other hand, show competitive performance across such long tail cases. The paper also shows that retrieval-based language model, which is indicated as red and green line here, shows much better performance than the standard language model, which is indicated as blue here. Many papers report similar findings across different language model, retrieval-based language model architectures. The NPM paper, which we discussed in section 4, evaluates the NPM model performance on Google RE task, where given the input, the model needs to predict the masked token. And they found that when the masked token is less popular, then the NPM model can still show really robust performance, while GPT-3 or like other large language model can still struggle. This effectiveness in long tail is not only in just short form generation or question answering. Another recent paper shows that retrieval-based approach can be quite helpful to reduce hallucination in long form generations. So this paper shows that Perplexity.ai, which uses the retrieval documents when it comes to generation, shows much more factually correct tendencies than other model, for example, InstructGPT or ChatGPT, which don't use any retrieval component. Another key effectiveness is knowledge update. So standard language models needed to be trained again to adapt to the evolving world knowledge. The Atlas paper shows model performance on Temp Llama dataset, which is a knowledge-proving dataset where the model needs to fill out the masked token, which can be evolved different over time. And they found that the fine-tuned T5 model without any retrieval component trained on older timestamp can struggle when we test the model on newer test data, for example, 2020 data. While in Atlas, which is a retrieval-based language model, they can simply swap the knowledge data store to accommodate such temporal changes without additional training. So here I show the performance of the model trained on 2020 data and using 2020 data store. And also the green bar shows that the model trained on 2017 data and using 2027 data store. And as you can see, even though there is a small performance deterioration from blue bar, still the green bar retains high performance without training the retrieval model or language model on new training data. So in summary, retrieval-based language models enables us to just simply swap the test data store without requiring any training to accommodate such temporal changes. Many papers also report that such retrieval-based language model can be quite competitive and even outperform much larger language model in fact completion task. So this paper shows that retrieval-based GPT Neo 1.3 billion outperforms vanilla GPT-3 on open domain QA task. And similar finding is reported by the NPM paper, where the NPM 354 million models outperform GPT-3 on the T-Rex dataset. On the other hand, it should be noted that in some tasks, still like retrieval-based language model using much smaller base language model struggle in some tasks. As we discussed in the Atlas paper section, the base number of Atlas and MM and U is still lags behind Chinchilla or like GPT-4 model. And there is still large room for improvement to build retrieval-based language model that can perform well in many different tasks. I also briefly talk about the verifiability or attribution of retrieval-based language model. So the Go4Cite paper and also the concurrent WebGPT paper provide citation or verified code in addition to the original answer. This is really helpful because human can now evaluate if the model generations are actually factually correct or grounded by this supporting evidence. So how effective retrieval-based language model is in terms of this verifiability or attributions? There's a recent paper called Attributed QA, which explores the effectiveness of attribution of different methods. So Attributed QA tests attribution, which is finding supporting evidence of language model output and evaluate whether the output is actually supported by the evidence. And they evaluate this attribution score, which is called AIS, using based on human evaluations and also automatic evaluations using trained natural language inference model. And they explored different approaches, including retrieval-based language model, which takes retrieved documents at the inference time, or post-hoc retrieval, which use language model but without retrieval at inference time and find the evidence in post-hoc manner. And the paper shows that retrieval in context approach or retrieval-based language models yield higher AI score based on human evaluations and also the model evaluations than post-hoc retrieval. This further indicates the effectiveness of retrieval-based language model for verifiability or attributions. So in this section, I talked about 4 effectiveness of retrieval-based language models, but there are many more effectiveness of retrieval-based language model. For example, in section 2, we briefly discussed that retrieval-based language model, such as KNN and LM, can be quite effective in out-of-domain adaptations, or many papers recently explored the effectiveness of retrieval-based language model in privacy. And if you are working on the task where those effectiveness are quite important, then you have the good chance of getting large performance improvement by using retrieval-based language model. And now I would like to move on to the last section before the conclusion. And also, if you have any questions, please feel free to post the question in Slido anytime, and we are actively answering the questions. And so I know like everyone is feeling tired, but this is the last section before conclusion. And so in this section, I will talk about the extension of retrieval-based language model for multilingual and multimodal context. So in prior sections, we mostly focus on retrieval-based language model using English text as data stores. But right now on the web, there is a diverse and heterogeneous knowledge available, and we would like to make the most use of those enormous amount of web data. So for example, even in just text corpus, we have many different documents written in different languages, and many knowledge is represented in many different modalities, such as like knowledge graph, video, audio, or image. And in this section, I'd like to talk about extension to multimodal, multilingual, and multimodal with a focus on training and architecture changes. So first, I'd like to talk about multilingual retrieval-based language model. So multilingual retrieval-based language model involves retrieving documents from different from data store written in different languages and generate based on these like documents written in different languages. Why it's necessary? Why we just build a retrieval-based language model using the same language as the input X? So the reason is that in many languages, we don't have that big data store compared to English. For example, here the question is here this Japanese question asks the origin of poutine, and if we only search documents from Japanese data store, then we might not have helpful information, and the model output may not be informative. Well, if our model can find documents across different languages, especially like higher resource languages like English, then we have a better chance of finding helpful documents. And the final output of multilingual retrieval-based language model can be more helpful and informative. But one challenge of building such multilingual retrieval-based language model is that there's a strong language biases in representation space. So when we naively encode documents using multilingual pre-trained model, the representation or the resulting embedding can be typically separated based on the languages. For example, here, those two documents are exactly same topic written in different languages. And we hope that those two documents will be located closely in embedding space. But in fact, those documents can be located closer to the documents written in different languages, but talking about completely different topics. So in this paper, they explored the effectiveness of multilingual retrieval-based language model and improved them by using iterative training of retrieval model and language model for multilingual question answering task. So in particular, to overcome the language bias issues in embedding space, this paper proposed iterative training of multilingual language model and retrieving component. So first, they fine-tuned retrieval model and also language model using task data. And then they keep expanding the training data by mining the new positive paragraph written in different languages using the Wikipedia's language links. And they filter out those new positive and negative paragraph based on these pre-trained language models and keep expanding the training data and training. They show that this new model gives large performance gain from fine-tuned language model with a retrieval, which is similar to the English retrieval-based language model. They also found that this new method can significantly outperform prior state-of-the-art method, which typically only use data store in single language. And this iterative training strategy can help the model to overcome the language biases and give us large performance improvement. And there are many new papers studying multilingual retrieval-based language models for diverse tasks, question answering or fact verifications, dialogue, and so on. And the fundamental key research question in those papers is that in many languages, we don't have enough data store, unlike in English. So our models need to learn to retrieve and generate based on such diverse multilingual documents. And lastly, I'd like to talk about multimodal retrieval-based language model. So here I show the multimodal, meaning the text and image, and I would like to provide some brief overview first. So in multimodal retrieval-based language model, we have index, which can be like text or which can be like image, and our multimodal retrieval model must handle those different modalities to find helpful documents which can be image or text. And then like our multimodal language model takes input X and then like those retrievable documents to generate output. And input, output, or retrievable document can all be multimodal, meaning like text or image. This new paper from Facebook conducts large-scale pre-training of retrieval-based multimodal language model. So the proposed method, RACMC, conduct large-scale pre-training of based on the prior method CMC. So this RACMC uses clip encoder to build a multimodal retrieval system. For example, given an input query, a realistic photo of Statue of Liberty standing next to Washington Monument, which is not existing. They first retrieve figures of Statue of Liberty and also Washington Monument. And then the multimodal transformer takes the input X and also retrieve the documents to generate the realistic photo as output Y. So I will skip the detailed training of these models, but the key idea is that they retrieve documents and they prepare these retrievable documents before the main document, which is pretty similar to our other architecture in like section 2, 3, or 4. And they show that this proposed method, RACM3, largely outperforms their base language model CM3 without any retrieval. And they also show that the proposed method largely outperformed the DALI 12 billion using much less parameters. By using much less parameters, they show that their method is much training efficient. And there are many exciting papers studying such multimodal extension of retrieval-based language model. So many papers conduct pre-training or fine-tuning to specific target task without focus on text or image. More recently, some papers explore extension for even new input or output modality. For example, using retrieval-based language model for molecular generations, or using retrieval-based language model for 3D motion generations. So wrapping up this section, I would like to emphasize that there are many interesting papers conducting extension of retrieval-based language model for multilingual or multimodal, and they show effectiveness, similar effectiveness as in English retrieval-based language model. So in multilingual context, we found that cross-lingual retrieval and generation can help us to overcome data source scarcity in many different world languages. And in multimodal, as we have briefly discussed, some key effectiveness like long tail or like efficiency has been also discovered in such multimodal context. So there should be many papers that can study such extension of multimodal to underexplored modalities. So now we would like to move on to the conclusion section.
Okay, so I hope that you have been enjoying all the content we prepared today. So at the end, I would like to quickly conclude our tutorial with some like challenges and opportunities, and hopefully we can have more time for Q&A at the end. So just a very quick recap of the tutorial today. So in the last couple hours, we covered all the basics and the recent developments of the retrieval-based language models, from the problem definition and to the model architectures, including what to retrieve, how to use retrieval, and when to retrieve. We also introduced 4 different types of the training methods for training the retrieval-based language models. So Akari also just introduced like different aspects of thinking about how to apply the retrieval-based language models to different applications, how to adapt, and when we should use these models, as well as the extensions like to the multilingual and multimodal settings. Okay, so what are still the biggest challenges and open questions today that for building the retrieval-based language models? So we believe that one of the bigger challenges is how to scale up these retrieval-based language models. As I mentioned at the beginning, our hope is that eventually we can develop retrieval-based language models with a smaller language model and a large data store that can be actually competent with a large parametric language models. So today we have actually introduced so many different types of retrieval-based language models. But the one important factor we haven't really discussed in depth is actually this trade-off between the size of the language model and the size of the data store. So as you can see from this table, today we have the models like Rachel, which use only a 7 billion language model, but a very large data store of 2 trillion tokens. And we also have models like Replug, which directly build on the very large language models like 175 billion models, but paired with like a relatively small data store. So moving forward, if we want to really build like a scale up this retrieval-based language models, build a very strong retrieval-based language models, what should be the right trade-off between the two sizes? So just like the parametric large language models, that in the last couple of years, people have been studying a lot about the scaling law of the parametric large language models, which means that we can actually approximate the training loss or evaluation loss as a function of the number of the training tokens, model sizes, or either the number of the training flops. So we believe that if eventually we want to scale up the retrieval-based language models, we also need to think about what should be the scaling law for the retrieval-based language models. That means that we also need to take the size of the data store into account if we think about the scaling law. Of course, this could be also depend on the like different model architectures and the training methods. So maybe before that, we will also have to figure out what should be the best model architecture and the training method, which is actually the large part of our tutorial today. And another like bottleneck or like a major area for improvement right now is actually also we need to think about the efficiency of the retrieval component. How can we actually do this kind of approximate similarity search more efficiently? So as you can see from this figure, this is based on a very small experiment. So language model has only 250 million parameters, and the data store has 100 million entries. So based on our measurement, you can see that if the KN language model, if you add just as an approximate search, is actually already like 12 times slower than the language model component. If we use the exact search, it will be 60 to 70 times slower. So this will be actually a problem eventually if we want to actually further scale up the size of the data store. So right now, this is actually a very active research area of exploring how we can actually conduct more efficient similarity search on the different accelerators, such as GPUs and TPUs. I actually believe that this will become one of the key factors for scaling up the retrieval-based language models. This is actually also very active research area across many different fields, including like machine learning, database systems, and so on. So this is actually a very important question. So there has been actually a lot of the really good developments for trying to solve this problem to actually speed up the search process of the nearest neighbor search. So I'm not going into any details of these papers, but if you're interested, I encourage you to check out these papers. And another middle ground solution that we already discussed in section 3 is actually so maybe sometimes we don't have to do the retrieval all the time. And we can really think about when we actually should do the retrieval and when the data store is actually necessary for us to use. So I don't have to talk more about this. Finally, I also want to briefly mention that the space efficiency might be also another bottleneck if we continue scaling up the size of the data store. If the data store becomes really large, this would actually require very large disk space for just storing the data store. So they will actually involve a lot of other design questions, such as should we actually store the vectors, or what kind of representations of vectors, or should we actually store the raw text of the data store on the disk? Okay, so this is about scaling. And another big space for open research questions is actually about applications. If eventually we can scale up these retrieval-based language models, can we believe that these models can be actually equally competent with a parametric large language models. So in section 5, we already have seen a lot of positive evidence and really good, good applications. But there's still a large space for exploration. There's still a lot of cases that we actually don't really know how to apply the retrieval-based language models. For example, the open-ended text generation is one of the most common cases or what people care about for like models like ChatGPT. So if you ask a question, the model can give you a very long, like a long and a coherent answer to these questions. So in this very recent paper, Wang et al. Paper, they actually did a study that they compared the GPT-2 model and the KN language model. And they found that the KN language model can achieve better perplexity, but it actually doesn't really guarantee like a better generation quality. So this is still an open question yet. So we are not sure if this problem is actually really because of exposure bias, or it actually means that KN language models actually need to require like better decoding algorithms that we actually usually use with parametric models. And another big aspect of the application is actually about the reasoning, about all these complex reasoning tasks. So this is also a very new paper. So this paper basically also provides like some arguments that they experiment with like a number of the retrieval-based language models. They found these models still struggle with a multi-step entailment or logical reasoning problems. So this could be either because the retrieving just based on the similarity of the queries is actually not sufficient for this multi-hop or the complex questions. Or this could be also because current language models might still struggle with synthesized information from the different multiple statements. Of course, there has been actually a lot of the really good papers coming out just in the last couple of months trying to address problems. So the solutions could be either through like an iterative retrieval and a query reformulation. Or the solution could be, let's say if the task is really complicated, can we decompose this task into like a multi-hop program for solving these problems? I don't plan to talk about any of these papers, but if you are interested, I encourage you to check out the papers I list here. Okay, so let me just conclude and try to reiterate these points we actually talk about today. So moving forward, we really believe that we need to figure out what should be the best architecture and the training method for retrieval-based language models in practice. So this is actually really a big part of today's tutorial. So after we figure out this point, we also need to figure out how to best scale up these models. Maybe our first step is trying to study the scaling law of these models. And now finally, we also believe that compared to parametric models, we also probably need to explore the alternative decoding or downstream adaptation methods for different downstream tasks. Again, I hope the content we prepared today would be actually useful for you, and I really hope that more and more people will be actually start working on these problems. Okay, so thanks for joining us today, and I think we still have at least 10 minutes for Q&A. If you have any questions, please come to the middle of the room for the microphone, and we are happy to take more questions. Thank you.
And also before starting the QA, we answered many questions on Slido. So if you post any question previously, please look at the Slido. And now we would like to take questions from this room and also over Zoom.
Well, you had this picture, you show this large language model and then small one with a large database. Right. And right. And the sentiment was that they probably can compete. So this small model with large database can compete with a large language model. But it feels that it might not be comparable, that they actually cannot, because when you train a large language model, when you train the small one with database, you optimize it for effect retrieval only for this one task, right? And then when you train the large one, it might get some other skills like reasoning, summarization, all that, right? So what do you think? If you Basically, my point is that this retrieval LLMs might be very specialized and good only for one task, the retrieval of facts. And then, so they are competing directly with large models rather than very niche solutions. What do you think?
Sorry, could you repeat the question again?
So what's your view? Because on one slide, you show this large language model and you say that it can compete with a small model plus database, right? And then do you think that they actually cannot compete because large model, when it trains on large corpus of data, it learns on not only retrieve the facts, but also do some other things like multi-step reasoning and summarization and all these other skills. And the small model, yes, it can compete with the large one in terms of facts retrieval, but it don't have all these other skills. So is that correct view, or you have different view on that?
Okay, thanks for the question. So our current belief is that probably we don't need such a large language model, and the smaller language model can be a core component for reasoning. And the most information we can actually put in the large data store. And I think actually Rachel is a good example. Rachel has only like a 7 billion size language model, but they use a very large data store. And they compare to GPT-3 and say, okay, they achieve comparable perplexity on the tile data set. But the problem is that the Rachel is really not a public model, so there's no way for us to test like models like Rachel on the downstream task. But in terms of like the applications like multi-step reasoning, I think it's likely that a smaller model will be able to cope with these problems. But all we need is actually to develop better prompting methods or better adaptation methods for these multi-step reasoning problems. So I actually mentioned like in some of these papers. Yeah.
Okay, thank you.
Thanks.
Hi, thank you for this informative tutorial. So this is a question for Danchi. You mentioned that in the future, the scaling behavior and scaling law for the retrieval-based language model will be very important. So I just want to ask, like, what are the kind of the intuition about the scaling behavior? For example, there's a Chinchilla scaling law where you need to scale the pre-trained data exponentially and the model parameter exponentially for the linearly increasing model performance. Will it be like similar to you need to scale up the outside memory exponentially to get a linearly increasing kind of downstream performance?
Yes, that's a very good question. I've been thinking about this question for a very long time, but I don't really have the answer yet. So, but we have seen a lot of evidence that if we just fix the language model, but scale the data store, the perplexity will be definitely decreased significantly. The question is, what should this curve look like? Honestly, I really don't have the answer for you today, but I also believe this perplexity result can transfer to the, for example, prompting or in-context learning for downstream tasks. But we will see. Hopefully, we will get the results very soon. Yeah.
Awesome. Thank you.
Hi, thanks for the great tutorial. In the NLP community for the last few years, we've been thinking about bias captured by the parameters of conventional language models. And I'm thinking about whether or what directions the community could go in understanding the biases in retrieval augmented language models as well. It seems a very new type of modeling formulation, and there hasn't been much work, as far as I'm aware, in this space right now. Like you could assume that editing bias for a retrieval augmented language model is just like deleting the information, but I don't think it could be as simple as that. So what would you suggest for the community and people interested in this bias and ethics space of NLP as well? Thank you.
That's a very great question. Thanks for asking. And yeah, I agree that bias and ethics problem is overall very important problem in NLP. And unfortunately, I think there has been no work that specifically look at this in retrieval language model context. But one naive idea I have is data store can provide more interpretability and explainability. So you can control and remove bias perhaps more easily by replacing or manipulating data store. That's my guess, but I think, yeah, we should actually show that's actually the case.
Thank you.
Hi, my name is Xinxi, and I have a question. So I was recently also doing some surveys on the small models. So I found there potentially is some challenges where the database or data store is not updated to the most latest data store or knowledge in the world. And potentially some large language model like ChatGPT, they can always get the most updated knowledge based on user feedback. So what's your thinking on how can all these small models solve these questions like this?
Thank you so much for a great question. Yeah, we agree that like data store can be also outdated, while like the parametric models can be like trained on up-to-date data. And I think one important aspect of retrieval-based language model is that, as we mentioned, like it has verifiability or attribution, and it provides like what kind of documents fit into the model. And also we know exactly like where the knowledge is coming from. For example, if we have knowledge, for example, like if we have like Wikipedia sources, we know like which one is like up to date based on the like the last edit history. And I think those meta information can be helpful to see like which data store is most up to date. While like in parametric approach, while like language model, also like those models can be uptrained and like the most recent pre-trained cohort, it doesn't mean like whenever like we ask those time-sensitive queries, the model actually like answers based on like the most recent knowledge. And I think the knowledge update itself is another big research area right now. And there are like many interesting open questions. Did I answer your question?
Yeah, I have just one small follow-up question. Do we have any research work to standardize all these source? I mean, the listing all the sources and updated work for the metadata in the industry right now? Since I think that would be very meaningful.
That's a great suggestion. We can probably maintain our website or like create another separate GitHub repo to actually maintain these resources.
Cool,
Yeah.
thanks.
Hi, thank you for the great tutorial. It was really informative. My question is this. So right now, one of the lines of research is trying to increase the context length of these transformer models, right? So they can process more and more text. So in terms of two directions, you can either we can do more retrievals of average based things, or we can do better retrieval of things that are more informative. Is there a viewpoint on which seems to do better for downstream performances, or is that still open as such?
Oh, there's a lot I have to go back to.
I'm sorry if I missed it in the talk.
Yeah, we understand the question. Okay.
So the question is why?
Then you should see what long context. Sorry, asking you.
So just to confirm, is your question like when we should use K-NAN search for long input modeling?
No, so my question is more like, given the large context window that we have, we can feed in more and more documents to fit in that context window, right? So you can retrieve a lot more neighbors to condition on for generation. Versus if you have a limited context window, you can improve the search retrieval to make sure the generations are faithful. So which direction seems to be more promising?
Oh, I see. That's a great question. And I think there is a trade-off. Like even if the transformer can process many blocks, the cost will still at least linearly. So if the retrieval quality gets better, then the inference time can be more efficient. Whereas if you care less about inference time, but really care about performance, and you have a model that can afford many text chunks, then that seems like a right way to do. So yeah, I think it's a trade-off, and yeah, it's still unclear what's the best trade-off, but yeah, I think that's a good, like, promising avenue for future work.
Thank you.
Hey, thank you for the tutorial. I found it very, very interesting personally. I have a couple of questions. So first, about the dimension of the encoder. So you talked a lot about the dimension of the language model on top of the encoder. So small language model plus retrieval can be very effective compared to a large language model alone. But what about the dimension or expressivity in general of the encoder itself, like smaller encoder? I mean, anything about your experience about this? I mean, like in some experiments that you showed, you always showed some results with the DPR style or something else. I mean, how much the dimension or the performance of the encode or the encoder, so the retrieval, affects the final result, or maybe the language model on top of the retrieval is much more important. I mean, anything about this?
Sorry. So just to clarify, so the question is that what is the effect of like increasing the model size of retrieval component?
Yes.
Okay.
Yeah. I mean, the retrieval compared to the language model on top of the retrieval.
Oh, retrieval compared to language model. So,
Yeah. I mean, the retrieval, so which is DPR style or something similar.
yes. So
Compared to the language model after the retrieval stage.
Oh, so just to confirm, you mean like a size of the parameters in the retrieval side and the language model side? Like how is there a trade-off?
Yes, but I don't refer to the dimension of the index itself, but the model that produces the index and encodes the entries of the index.
Yeah, I think there is a few papers that show that as you increase the model size for the retrieval system or increase the dimensional size of the dense vector, then the performance will get much better. I'm not sure if people have looked at the exact comparison to like regular language model. My guess is that the gains by using larger model would increase a bit slower than language model because retrieval is basically more of a lookup model rather than needing to memorize things. Yeah, does it?
Yeah, I have the same perception. Just wanted to know if you have some evidence or something extra. My second question is about the latency in inference. About the scalability, I think, unless I missed something, my understanding was that the retrieval part, because of the dimension of the index, because of the encoding, so the retrieval part can be a bottleneck. So I wanted to know more about your experience with this, because I think intuitively and also partially based on my experience, that part is the fastest in inference. So the encoding part, because of almost everything is pre-computed, and the similarity between input questions and the index can be computed quite easily. I'm not sure if that is the bottleneck, because it's quite fast. So in terms of a few milliseconds, you can found even an exact search based on 100 millions of documents. So I wanted to know more about that.
The efficiency of Oh, yeah. So I guess the question is about the latency coming from the retrieval part. Yeah, we have showed in one of the work that adding the retrieval will actually hurt the speed. So that's based on when we have a when we have a similar size of the language model and the retrieval model, and we can imagine that at the end of the day, we want to use a larger model where we keep the retrieval retrieval side dimension small. And in that case, the effect from the retrieval part will not that large. And also, because the KN search is actually a very fundamental problem, and they have been a lot of well-developed tool, and it can be run in parallel. I think we have a lot of solution to speed up the retrieval part.
Okay, okay, thank you.
Yeah, thank you so much. So for so many, oops, sorry. Thank you so much for many great questions. And the instructors will be here. So if you have any additional questions, please feel free to come to us after this session. And yeah, like, thank you so much for attending today.